In this video, we will use simulation experiments to provide an easy-to-understand explanation on the effectiveness of isolators, which are an indispensable component for analog signal interfaces. Many I/O interface circuits designed to handle analog signals are contained in instruments such as industrial process instruments, measuring instruments, IT instruments, and medical instruments. Isolators are signal conditioners used to separate galvanically or isolate between the inputs and outputs of analog signals to prevent equipment malfunction and damage. Isolation is also very important for avoiding the risk of electric shock in medical instruments and measuring instruments handled by humans. Isolators can resolve various problems with signal loops or prevent them from occurring in advance. Now, let's examine the actual effects of isolators in breaking ground loops, preventing signal noise effects, and protecting equipment from damage. First of all, what exactly is a ground loop? As an example, this shows a signal loop in which instrument 1 in a control room is used as a receiving instrument for the signal source of the field, with the negative side of this instrument being grounded. If instrument 2 is added to view this signal in the field and the negative side of instrument 2 is also grounded, the current will loop via those two grounding points. This would result in current not flowing normally to instrument 1 on the downstream side. This problem can be avoided by inserting an isolator between the signal source and instrument 2. Let's test this theory. Here, 2 meters are connected to a current simulator that serves as the signal source. The 2 meters can be grounded by being connected to a metal plate that serves as a ground. Although a base socket for the signal conditioner is located in the middle, it will be bypassed to prevent the signal from passing through it. In this state, the current simulator and meters are directly connected without passing through the base socket. The ground wire of the meter 2 on the upstream side is removed, creating an open circuit between the negative side of the signal line and the ground. Now, only meter 1 on the downstream side is grounded. 20 milliampere DC is then applied using the current simulator. Both meters show 20 milliamperes. As can be seen, no problems occur if the signal loop has only one grounding point. Next, the negative side of the signal line of meter 2 on the upstream side and the ground are connected. Although meter 2 on the upstream side shows 20 milliamperes, meter 1 on the downstream side now shows 0 milliamperes. Because there are 2 grounding points, the signal stopped flowing to meter 1 on the downstream side. We will now install an isolator to this signal loop. First, the input line connector is connected to the base socket. The isolator is then plugged into the base socket, and 20 milliampere DC is applied. By inserting an isolator, both meters now correctly show 20 milliamperes. There may often be situations when you want to add a local indicator to an existing signal loop with a recorder. Or there may be times when you can't determine the loop grounding point due to it being an older system. Using isolation in situations such as these can provide peace of mind. types of noise include normal mode noise and common mode noise. In many cases, it is common mode noise that affects the operation of electronic circuits and becomes problematic. Common mode noise is noise that is applied between the signal source and the ground. In this state, because noise is applied to the circuit on the receiving instrument side and at the same potential, it exerts no effects. However, were current to flow from the receiving instrument side to the ground through parasitic capacitance, in turn causing the potential balance with respect to the ground on the receiving instrument side to be lost, the potential difference would appear as normal mode noise at the circuit on the receiving instrument side. Parasitic capacitance is an invisible capacitive component. Here, by inserting an isolator to block the intrusion of common mode noise into the receiving instrument, any effects on the receiving instrument can be eliminated. Let's test this theory. Here, a voltage simulator that serves as a 1 to 5 volt DC signal source is used, with 1 megaohm being connected instead of a receiving instrument. On the receiving side, an oscilloscope is also connected. For the purpose of this experiment, resistors of 100 ohms are added to simulate lead wire resistance, which is larger than it would actually appear. A parasitic capacitance of 0.2 microfarad is then installed between the negative side of the signal line on the receiving side and the ground, causing the balance between the positive and negative sides of the signal line with respect to the ground to be lost. Although a base socket for a signal conditioner is located in the middle of the signal line, the signal will be bypassed by connecting the connectors of the input line and the output line. First, 1 volt DC is generated using the voltage simulator. It can be confirmed to be 1 volt on the oscilloscope. Next, by increasing to 2 volts, 3 volts, 4 volts, and 5 volts, the waveform changes in steps, but no noise occurs. Here, to generate common mode noise, a 100-volt AC mains supply is applied between the negative side of the signal line and the ground. Although the waveform was straight a moment ago, it is now highly disturbed, showing that the noise of the AC component is superimposed on the signal line. Changing the input signal by 1 volt also causes the waveform with noise to move. We will now install an isolator to this signal loop. The base socket bypass is first removed, after which the isolator is plugged into the base socket. It shows 5 volts. A 100-volt AC mains supply is then applied again to generate common mode noise. Because the isolator blocks the noise, the oscilloscope waveform doesn't change, and only the 5-volt DC component appears. Although the waveform changes in steps when the input signal is changed by 1 volt, it is not affected by noise. Cables laid in the proximity of generators or large transformers attract signal noise, which may cause false operations of an instrumentation system. Using isolation in situations such as these will ensure accurate measurement. In common mode, intrusion by noise strong enough to damage equipment can sometimes occur. As an example, let's examine what effects an isolator has when lightning surge voltage intrudes in common mode. This meter is connected to a voltage simulator that serves as a 1 to 5 volt DC signal source. To confirm the flow of surge current, a 300 milliampere fuse has been installed on the negative side of the input signal. This is a lightning surge simulator, which is a device capable of applying a surge voltage of 2000 volts between the negative side of the signal line and the ground in common mode. The isolator is plugged into the base socket. In this state, the isolator is installed between the signal source and meter. Also, an oscilloscope is connected between the negative signal line on the input side of the isolator and the ground. First, 5-volt DC is generated using the voltage simulator. It can be confirmed to be 5 volts using the meter. Here, a surge voltage of 2000 volts is applied between the negative side of the signal line and the ground. A surge waveform of 2000 volts appears on the oscilloscope on the input side. However, no change is shown on the meter. This is due to the effects of the isolator. We will now remove the isolator from this signal loop. The base socket will be bypassed. The meter shows 5 volts. A surge voltage of 2000 volts is applied again. The meter display is no longer correct. The current from the lightning surge flowed to the negative side of the meter input, causing a blown fuse. Although lightning surge voltage was used in this experiment as a strong noise for intrusion in common mode, because actual intrusions by lightning surges occur in both common mode and normal mode, lightning surge protectors are required. Noise from strong electromagnetic fields and high-voltage impulse noise caused by lightning surges may be superimposed on signal lines from field equipment located in hostile environments where various electromagnetic fields exist. Using isolation in situations such as these will protect your receiving instruments. As shown by these 3 experiments, isolators can have a powerful effect. Using isolation can protect equipment from malfunction or damage and prevent risks of electric shock to humans. Furthermore, by passing signals between devices from different vendors via an isolator, the boundary point of responsibilities can be made clear even when a system failure occurs. M-System offers over 200 models of isolators, from plug-in types to onboard isolation amplifiers. With isolator output signals, connections to any type of equipment can be made with peace of mind. Isolators are an indispensable component for analog signal interfaces. We would like to recommend the use of isolators.
Thank you for watching.